In this short video, we'll explore subtypes of light, electron, and scanning probe microscopes, how each works, and what it's used for. First up, light microscopes. We're going to be covering these forms of light microscopy: bright field, dark field, phase contrast, differential interference contrast, fluorescence, confocal, and two-photon microscopy. Bright field microscopy is what most people mean by a light microscope. Bright field microscopy shines white light straight through a sample. Parts that absorb more light look darker, so it's great for viewing stained cells or tissues. Dark field microscopy is like the opposite of bright field. Dark field microscopy casts a hollow cone of light that misses the lens entirely. So, only light scattered by the specimen reaches the objective, making unstained microbes glow bright on a dark background. In phase contrast microscopy, refractive index differences in the specimen, known as phase shifts, generate contrast so you can see live, unstained cells and subcellular structures. In differential interference contrast, or DIC microscopy, polarized light is split into two beams that scatter differently as they pass through the sample. When they recombine, their interference creates a 3D shadow effect that highlights cell edges and surfaces. Fluorescence microscopy uses dyes that glow under the right light. You attach the dyes to specific molecules like bacterial proteins to see where they are in the cell. Its main advantage is target specificity. In confocal microscopy, a laser scans the sample point by point to digitize sharp optical slices. A computer then uses those data points to build a 3D view of subcellular structures, much like rendering a video game model, pixel by pixel. In two-photon microscopy, two weak infrared beams pass through tissue without exciting the dye. Where they intersect, constructive interference boosts their combined intensity enough to excite the dye, enabling deep imaging of cells in live, small organisms. So far, we've covered microscopes that shine light through a sample, but other kinds of microscopes gather information using different methods. For example, electron microscopes fire a beam of electrons instead. Because electron waves are far smaller than light waves, you can see much tinier details. Scanning electron microscopy, or SEM, scans the surface with electrons and collects scattered electrons to map surface details. Transmission electron microscopy, or TEM, shoots electrons through a sample to reveal internal structures at the nanometer scale. Scanning electron microscopy is beautiful, but all these images are artificially colored, because electrons don't carry color information like light does. Scanning probe microscopes drag a tiny tip across the surface. Scanning tunneling microscopy, or STM, essentially listens for electrons that jump between the sample and the sharp tip. Atomic force microscopy, or AFM, feels the surface like a record player. That's your tour of light, electron, and scanning probe microscopes. Each method lets us explore microbes in a different way, so we pick the one that fits our sample and question.